A trampoline may seem like it utilizes complex physics concepts. However, almost all the science under jumping on a trampoline can be summarized by the equations on our equation sheet. There are a lot of ups and downs, but it really is not at all that bad. With that said, let's jump into action. The magic behind jumping on a trampoline lies in its springs. They're what gives that extra hop. The most obvious equation regarding the mechanics of trampolines, then, is Hooke's law. While it is true that springs on the trampoline have mass, exhibit dampening, and therefore do not act as ideal springs, Hooke's law is still important in analyzing springs in the physical world. So, to reiterate, Hooke's law states that an ideal spring is one whose spring force relates linearly to the distance it is displaced from equilibrium. In non-ideal springs, this simply means that a typical spring's force will relate near linearly with the distance displaced from equilibrium. With that in mind, how does a trampoline actually launch one into the air? How are the spring forces used to give Evan that extra jump? To understand this, we must first inspect the meaning of energy. Work is the application of a force through a distance, whereas energy is the capacity for doing work. Another way to think about this is that the change in energy of a system is work. Both are measured in joules, which is equivalent to the work done by a force of 1 Newton acting over a 1 meter distance. But what if that force isn't constant? Like in the case of an ideal spring or near ideal spring, the force at each moment is affected by the distance at which the spring is displaced from equilibrium. In this case, we have to add up all the little bitty forces applied by the spring at each distance in order to get the total work, a process often used in defining integrals. And with that, we finally arrive to the equation for the potential elastic energy of an ideal spring. This equation, in fact, is the integral of Hooke's law. It adds up all the forces built up within the spring in order to evaluate the total amount of energy within the spring object Earth system. This represents the elastic potential energy of the Earth mass spring system. U is commonly used to represent potential energy. So the elastic potential energy of the spring is equal to 1/2 times K, the spring force constant, times x, the distance displaced from equilibrium squared. Now finally, let's get into a real problem. A group of 4 friends, each a mass of 50 kilograms, are jumping on a trampoline. The trampoline is circular with a radius of 2 meters and has 40 springs around the edges. Each spring has a spring force constant of 30 newtons per meter. If all friends are jumping close to the middle in one clump, and if they all jump at the same time to a height of 2 meters, how far will the friends go down into the trampoline? Assume the tarp of the trampoline does not stretch a significant amount. In order to solve this problem, we want to use our equation for the potential energy of elasticity. How we will use this equation is that the potential energy of elasticity when the springs are stretched its highest amount will be equivalent to the potential energy of gravitation when the friends are 2 meters in the air. With that, we can say that the potential energy of gravitation at the highest point will be equivalent to the mass of the group of friends times g, baby g, times delta h. Using that formula, we can use some simple plug and chug to find the potential energy, or at least gravitational potential energy, of the friend group Earth system. Now that we have the potential energy of the system, we can go ahead and try to find x. Keep in mind that because there are 40 springs in the system, or 40 springs surrounding the trampoline, that you must also multiply the right side of the equation by 40. We need to be careful, however, because the x squared, oh no, the x squared is not actually the vertical displacement of the spring, but the displacement of the spring as at an angle. We want to find out this value, which we will name y. This value right here will be the length of the spring plus however much it is displaced. For the purpose of this problem, we know that the radius of the trampoline is 2 meters. So we can assume that the length of this leg will be 2 meters as well. And then therefore the length of the hypotenuse will be 2 meters plus the amount it is displaced. Upon further review of this question, I'm not actually entirely sure that this equation has a real solution.